Assalamu alaikum students, welcome to our third lesson on quantum physics. Today we are going to discuss the subtopic of electron energy levels. So we will start with our discussion on identifying electron volts as a unit for expressing energy. Then we will explain electron energy levels and transitions between the levels, and finally we will analyze line spectrum obtained as a result of electron excitation or de-excitation. And you can see there is a lot of new vocabulary that we will be using today. So let's get started. First of all, we are going to define a unit known as electron volt. So what is an electron volt? So basically electron volt is nothing but a unit of energy. Now, we already know there is a standard unit of energy which is known as joules. So when we already have a unit of energy, why do we need another alternative unit of energy? So the answer lies in the fact that when we talk about subatomic levels, or when we talk about electron energies or photon energies, single photon energies, we are talking about really small values of energies. So for example, the energies that we talk about at subatomic levels could be, let's say, 2 into 10 to the power minus 15 joules, or it could be 1 into 10 to the power minus 18 joules. Now, as you can see, these are really small values of energies when we measure them in joules. So we have another alternative unit of energy which is more appropriate for using at smaller levels. And how do we define that unit? Let's discuss that. Let's assume we have an electron which is moving between 2 points A and B, and there is a potential difference of 1 volt between A and B. So our electron moves between a potential difference of 1 volt. Now, recall the definition of potential difference. What is potential difference? Potential difference is equal to the amount of work done per unit charge. So I can write it as work done per unit charge. And the charge that we are using here is the charge of an electron. So work done per electron, or the energy of an electron when it moves between point A to point B. So now, if I try to calculate the work done here in moving the electron between point A and B, how can I calculate that? I can calculate that as the potential difference between point A and B multiplied by the charge of an electron. So the potential difference we said is 1 volt. Charge of an electron is 1.6 into 10 to the power minus 19 coulombs, the elementary charge, right? So this gets us an answer of 1.6 into 10 to the power minus 19 joules. Now, why did I get work done in joules? Because I used the standard units for PD, voltage, and for the charge of an electron, which is coulombs. So volts into coulombs gives us joules, just like joules per coulomb gives us volts. So volt is nothing but joules per coulomb multiplied by coulombs gives us joules. So this is the work done in moving an electron between 2 points which have a potential difference of 1 volt between them. Now, this amount of energy is basically defined as 1 electron volt. So 1 electron being moved between a potential difference of 1 volt. This is what we call as 1 electron volt. And this also gives us the conversion between electron volt and joules. So if we have joules and we want to convert them into electron volts, we divide the number of joules by the conversion factor, which is 1.6 into 10 to the power minus 19, which is not hard to remember because it is the same as the charge of an electron, or the elementary charge. Similarly, if we have our value of or our energy in electron volts and we want to convert it into joules, we just multiply the electron volts by the conversion factor, 1.6 into 10 to the power minus 19. We're going to talk about energy levels or states of electrons in an atom. Now, to understand this, let's quickly recall the structure of an atom. We have studied the structure of atom in chemistry and physics of IGCSE, and we already know the basic structure of an atom as there is a positive nucleus which contains protons and neutrons, and then there are negatively charged electrons which are really small in size outside the nucleus. Now, the kind of a structure that you see over here, it's kind of like a solar system kind of a structure where the sun is at the center and the planets are around it. Actually, electrons in an atom don't really exist like planets do in a solar system, but this model is simple enough and easy enough for us to be used in our discussion today, so we will stick to it. It's a very simplistic model. So what do we see in this model? We see a nucleus at the center over here, and we see electrons in multiple paths or multiple orbits or multiple levels outside of the nucleus. Each level here we call as energy level. So what does it mean? It basically means that the electrons outside the nucleus, each electron possesses some energy or exists in a specific energy level. In order to move from one energy level to another, the electron will either gain some energy or lose some energy. So if an electron is in a lower energy level, it will need to absorb some energy to move to a higher energy level, or if it exists in a higher energy level, it will have to lose some energy or emit some energy to move to a lower energy level. So now these energy levels basically are fixed energy levels, which means that at each energy level, the electron needs to possess a specific amount of energy. So for each energy level refers to a specific energy. So electron existing in a particular energy level will possess a certain amount of energy. And what happens if an electron contains energy between, which refers to an energy between any of those two levels, any of these two levels? Well, that is not possible. An electron will always exist in one of these discrete energy levels. It cannot exist between these energy levels or states. So let's find out more about it. At this point, you can actually pause the video and go through the slide once to get familiar with certain terminology levels. So we said that in an atom, electrons exist in a specific energy levels outside the nucleus, which means that these energy levels are all quantized, or that the electron energies are always quantized. And if you recall the meaning of the word quantized, we discussed it when we were discussing the definition of a photon, or what is a photon. We said it's a packet of energy or it's a quantum of energy. Quantized means it will always have a specific discrete value. So what happens when electron moves between any two energy levels? So when electron transitions from a lower to a higher energy level, it absorbs a photon because it needs to gain energy. So how does it gain energy? It can gain energy by absorbing a photon. Now again, recall our previous lessons in quantum physics. We always said that one photon at a time can only interact with one electron. And we also said that when a photon interacts with an electron, it has to be completely absorbed by the electron, right? So when an electron wants to go from a lower to a higher energy level, it will absorb one full photon. And keep in mind, an electron cannot absorb half a photon or a quarter of a photon. Why? Because a photon itself has an energy which is given by E equals hf, where f is the frequency of the radiation. So this is the amount of energy it carries with itself. So either this whole energy can be transferred to an electron, or it will not be transferred to the electron. So one photon versus one electron always. Now, this process of an electron gaining some energy and hence jumping to a higher energy level is known as excitation of the electron. It gets excited. But when an electron is in a higher energy level and it wants to move to a lower energy level, what will it do? It will release or emit a photon. Again, what is a photon? It's a packet of energy. So how much will be the energy carried by this emitted or radiated photon? It will be equal to E equals hf, again f being the frequency of the radiation. And this energy of the photon will be equal to the difference in the energy between the two energy levels. And this process of an electron jumping from a higher to a lower energy level is known as de-excitation. So going from lower to higher energy level by absorbing a photon is known as excitation, whereas going from a higher to a lower energy level by releasing a photon or emitting a photon is known as de-excitation. And in each case, the energy of the released photon or the absorbed photon is always equal to the difference in the energy between the two energy levels between which the transition is happening. And this is called energy level transition basically. Now, each transition always corresponds to absorption or emission of a specific frequency photon. So it will always be either one whole photon is emitted of a specific frequency or one whole photon is absorbed of a specific frequency. And there is an illustration over here. It's an electron in a higher energy state or a higher energy level which releases a photon and hence jumps to the ground state. Ground state means lower energy level. So what do we get to see as a result of these transitions, or how do we get evidences of these transitions of electrons from between different energy levels? So what we get as a result is a spectrum a spectrum of radiations, a spectrum of different colors. Now recall what is a spectrum. So we have learned previously electromagnetic spectrum. What is electromagnetic spectrum? We have seen it in many times and since IGCSE that electromagnetic spectrum is basically a collection of all the frequencies that exist within the electromagnetic radiations that represent the electromagnetic radiations, and when we kind of arrange them in an order of increasing frequency or increasing wavelength, we get a whole spectrum of the electromagnetic radiations. And within that electromagnetic radiation spectrum, we have the visible light spectrum, and in the visible light spectrum we usually have different frequencies corresponding to different colors. So we starting from the highest frequency, we have violet, indigo, blue, green, yellow, orange, red, though you don't need to particularly remember all these colors, but you need to remember that violet corresponds to the highest frequency and red corresponds to the lowest frequency. So this is the spectrum of the visible region, and it's a continuous spectrum. What do we mean by a continuous spectrum? That all the possible frequencies between the frequency of violet and red that you can think of exist in this spectrum of visible light. And if I go to the next slide, I can show you a glimpse of what do I mean by continuous spectrum, the one shown over here. So you can see going from violet to red, we have got all the possible frequencies or wavelengths, and each particular frequency or wavelength corresponds to a specific color. So this is a continuous spectrum. So now think about the photons corresponding to each of these frequencies. So each frequency basically each frequency will have a photon carrying some energy corresponding to that frequency. E equals hf. So when atoms which have electrons in higher energy levels, or when electrons in these excited states get de-excited or fall back to lower energy levels or lower states or ground states, they emit a photon. And we already said that the photon emitted will always have a specific wavelength. So if an atom has multiple energy levels and there are transitions happening between these energy levels from higher to lower energy levels, there will be photons emitted only of a specific wavelength or a specific frequencies, so what we get at the output is a line spectrum and not a continuous spectrum. Why? Because the spectrum obtained as a result of these de-excitation of electrons or emission of photons will consist of only specific certain frequencies, unlike the entire continuous frequencies of the visible light spectrum. This kind of a spectrum is known as the emission spectrum. The emitted light can be observed as a series of colored lines with dark spaces between. The kind of spectrum we are talking about is the emission spectrum, which is a discrete spectrum, which is a line spectrum, not a continuous spectrum. So similarly, when the opposite happens, which means electrons get excited from a lower to a higher state, they will be absorbing photons, and the photons they need to absorb will always be of certain frequencies again. Therefore, the absorption spectrum will always be a line spectrum. So basically, there are two types of spectrum associated with each type of an atom or each element or each material. One emission spectrum, one absorption spectrum. You get to see an emission spectrum when photons are being emitted. And in what situation photons get emitted by electrons? When electrons get de-excited or jump down from higher energy levels to lower energy levels, or from excited states to ground states. Similarly, we get to see absorption spectrum when electrons jump from lower to higher energy levels by absorbing photons, which means from lower energy levels to higher energy levels. So this is how an absorption spectrum looks like. So what do we mean by an absorption spectrum, or how do we get it? So imagine we have a chamber, let's say, where we have filled in some gas. And we, on one side of the chamber or one side of the tube, we have a source of, let's say, white light. White light, we know, has a continuous spectrum, consists of all the different frequencies or wavelengths that you can think of in this continuous spectrum of visible light. We pass this white light through this gas, and when the white light passes through the gas, it transmits out from the other side, and we receive this light on the other side and pass it through a spectrum analyzer. A spectrum analyzer means anything which is capable of splitting white light into its constituent frequencies. And if you think about it, anything as simple as a prism can work as a spectrum analyzer, because we know when white light passes through prism, it splits up into its constituent wavelengths. Or another example of a spectrum analyzer which we have learned about in our curriculum is a diffraction grating. Remember when white light passes through a diffraction grating? Because each color or each frequency gets diffracted differently. Therefore, we can split white light into its constituent colors. So when the transmitted white light through this gas is passed through a spectrum analyzer and we break it apart into its different constituent wavelengths, we will see that there will be certain wavelengths missing, like shown over here in the absorption spectrum. You can see the black lines. The black lines are the missing wavelengths. Where did they go? These photons were absorbed by the electrons in the atoms of the gas filled in this chamber. And what did the electrons do with these absorbed photons? They used the photons to get excited, jump to higher energy levels. Here in this illustration, we see how excitation and de-excitation of electrons results in emission spectrum being formed and absorption spectrum being formed. So pause the video and take a moment to have a good look at this illustration, where the first one shows electrons jumping down from higher to lower energy levels, and as they do so, any jump between any two energy levels results in the release of a photon of a specific frequency, and the energy of the photon released is always dependent upon its frequency. It's a function of its frequency given by E equals hf, and the energy of the released photon is always equal to the difference in the energy between the two levels. Similarly, in the other illustration where you see the absorption spectrum, you see how electrons, when they jump from lower to higher energy levels, from ground to excited states, they need to absorb certain photons. And again, the photon energy is given by hf, so they can be only specific energies of photons that will be able to produce these transitions. Why? Because the photon energy needs to be equal to the difference in the energy between the energy levels. On this slide, we get to see the basic definitions of all the important key terminologies that we need to understand, that we need to know in order to understand this topic and in order to explain our answers. So let's just quickly go through them. Number one, energy state or energy level. What is it? What do we define? How do we define it? Quantized energy state of an electron in an atom. What do we mean by quantized? Quantized means having a specific amount of energy. It cannot have just any random amount of energy. A specific discrete amount of energy an electron will possess when in a specific energy level. Ground state, the lowest energy state that can be occupied by an electron in an atom. Excited state, the higher energy state where an electron jumps to after absorbing a ionization energy, which is the amount of energy needed to completely remove an electron from an atom. So we know that electron exists in different energy levels in an atom. Ionization energy will also be different for each of these energy levels. So for example, if an electron is closer to the nucleus, then a greater amount of ionization energy will be needed to remove it completely from that energy level. But if an electron is already in a higher energy level where it is not very close to the nucleus, not very tightly bound to the atom, does not have a high force of attraction electrostatic force of attraction between the electron and the photon and the nucleus, in that case the ionization energy will be smaller. So energy levels of hydrogen atom have been shown over here. Keep this in mind that energy levels are specific to a certain element, which means each element has its own absorption and emission spectrum, which means that if you have hydrogen, whether on Earth, in the sun, or anywhere in the galaxy, on any star, a hydrogen atom will always have a specific energy levels with certain specific energy values. Therefore, the emission and the absorption spectrum for a hydrogen atom will also be the same, regardless of where does this hydrogen atom exist. So all the hydrogen atoms, electrons will always need the same energy photons to undergo excitation, to jump from low to high energy levels. Similarly, for all the hydrogen atoms, electrons will emit the same energy photons when jumping from higher to lower energy levels and hence getting de-excited. So the spectrum that we receive for a particular element is always going to be the same. You can see this written over here on this slide as well. Each element produces a unique set of spectral lines. No two elements emit the same set of spectral lines. Therefore, elements can be identified by their line spectrum. This brings up let's have a final look at the energy levels of a hydrogen atom. You do not need to memorize any values. So we start from the bottom, and you can see there is an arrow pointing up, which means that at the bottom we have the lowest energy level, and then as we go up, we are showing higher energy levels. Let's have a brief look at the numbers shown. So the lowest energy level is shown to be at minus 2.18, and here the energies are shown in joules. So each energy level is basically showing the number shown over here multiplied by 10 to the power minus 18 joules. Mostly the energy for energy levels is given in electron volts. 2.18 into 10 to the power minus 18 joules is the value of the ground state, or the first energy level. As you go up, the number becomes a smaller number. The magnitude looks smaller. Why is the magnitude smaller? Because we know, remember we said that how much energy is required externally to remove an electron from a particular energy level. That amount of energy we label as the energy of a particular energy level. So if you want to remove an electron from the ground state of an hydrogen atom, from the first energy level, or we can call it the lowest energy level, which is basically an energy level or an energy state which is closest to the nucleus or the ground state, we need the maximum amount of energy. And since we are providing that energy externally, we write it down with a negative sign, minus 2.18 into 10 to the power minus 18 joules. So there is a large magnitude of energy we need to remove an electron from this energy level. But as we go higher to higher energy levels, we are moving away from the nucleus. So just look at the magnitudes, the numbers of the energies. The negative sign only shows that it's an externally provided energy, but the numbers show the energy value of that energy level. So for the next energy level, external energy of 0.54 into 10 to the power minus 18 joules is needed to remove an electron completely out of the atom when it exists in this energy level. And as you keep going higher and higher, the energy required to remove an electron from this atom becomes lesser, which makes a lot of sense because as you go higher, you're moving away from the nucleus. Therefore, the electron is not very tightly bound. So this is how energy levels of hydrogen are given. They could be given in joules, they could be given in electron volts. And when you're finding ever the difference of energy between any two energy levels, you can use the negative sign as it is and find the difference. For example, if I want to see that when an electron of hydrogen atom wants to get excited, or it's getting excited and it jumps from the ground state to the from the the first energy level, let's say, to the second energy level, then what energy photon does it need to absorb? So I need to find out the difference between the two energy levels. So how will I find that out? Just take the difference between the two numeric values, which means 2.18 minus 0.54, and I will get an answer of 21.26, and we also have the 10 to the power minus 18. 10 to the power minus 18 with every value. So this much amount of joules are needed. Similarly, what if the photon has slightly more than this energy, has an energy slightly more than this required energy, but it does not really correspond, or it does not really equate to any specific energy difference between any two specific energy levels. So keep this in mind. Until and unless a photon possesses an energy exactly equal to the difference in energy between any two levels, it will not be absorbed for excitation. Why? Because a photon can either be completely absorbed by an electron or not absorbed at all, and one photon at a time only interacts with an electron. Now let's answer some questions to understand this really well. So these are some exam style questions. First question is a multiple choice. The diagram shows some of the energy levels of hydrogen atom. You can see these are the energy levels, and here the energy levels are shown in electron volts. An excited electron in the level minus 0.54. Minus 0.54 means here the topmost, the highest energy level, drops to the level minus 13.60 electron volts, resulting in the release of at least one photon. At least one photon means it could release one photon or perhaps more. First of all, let's understand why would it ever release more than one photon. So let's assume that this photon jumps directly from the highest level to the lowest level, or the ground state. In that case, it will emit a single photon, right? But transitions do not necessarily happen as a single step transition. Transitions can happen in multiple steps. For example, the electron can first jump to the second level, and then from the second level down to the ground level, or it can jump to the, let's say, the third highest level, and then to the lowest level, or the transition can even happen like this. So in each of these situations, there can be more than one photon released, right? So now what the question is about is, which of the following photon energy values could not be produced from this electron transition? And we have some values here. So what we can do is simply we can just find the energy difference between the given levels and see that which of the photons there is a possibility of for which values of photons to be emitted. So for example, if I calculate the energy difference between the highest level 0.54 and 13.6. How do I do that? 13.6 minus 0.54, get a value of 13.06 eV. So this jump from the highest directly to the lowest level will release a photon of 13.6 eV. Now if you look in the answer options, that's already option D. So option D will be released. So we cannot say it could not be produced. It can be totally produced. Now for the second transition, let's say when it jumps from 0.54 level to 0.85 level, I can find the difference between 0.54 and 0.85 by doing bigger minus smaller, 0.85 minus 0.54, and I get a value of 0.3 eV. So in case the transition is a two-step transition, 0.3 eV is also one of the answer options. So it can be totally produced. It cannot be the correct answer here. Now if it's a two-step transition, so from the second level all the way to the bottom, if I find the difference between 0.85 and 13.6 for this jump and 13.6 eV, I get a difference of 12.75 eV. I will write it here with the transition. 12.75 is not one of the options. Now moving on to the next transition, when it moves from 0.54 to 1.51 and then to the lowest level. So the jump from 1.51 to 13.60 energy level will give you a value of, this transition will be 12.09 eV, which is one of the answer options. So again, it can be totally produced, whereas the jump from 0.54 to 1.51 will give you a value of 0.97, so which is not one of the answer options. Now for answer options, we already have three answer options as the energy difference between the specific energy levels which are being asked, which have been shown to us in this question. 0.54 electron volt, on the other hand, is one value that we did not calculate, so shows us that it has to be the correct answer. So the answer is B, because all the others we know, we already saw that are going to be released as a result of transitions or de-excitation of electron between any two of the given energy levels. Moving on to the next question, which is a 4-marker. The diagram shows some of the energy levels for an atom of hydrogen. Again, hydrogen, we see the energy levels. So the lowest energy level and then the highest energy level at the top. An electron with a kinetic energy of 12.3 eV interacts with this atom. So they're talking about an electron which is not part of this atom, but it is a moving electron. How do I know? Because they have shown me a kinetic energy value of this electron. It interacts with this atom. An electron in the atom moves from minus 13.6 electron volt level to minus 1.5 electron volt level, from minus 13.6 to minus 1.5. So basically there is an electron, an external electron containing possessing some kinetic energy. It interacts with the atom. As a result, an electron within the atom gets excited by absorbing some of the energy. How do I know it absorbs some energy? Because we know excitation always requires absorption of energy. So it moves between two energy levels. Okay. What does the question say next? When a photon with a photon energy of 12.3 eV. So now we have a photon, which is a packet of energy, and it also contains the same energy as the kinetic energy of electron in the previous part, right? In the previous statement. When a photon with a photon energy of 12.3 eV is incident on this atom, the electron in the atom at minus 13.6 electron volts, same electron, same energy level, the ground state, remains in the minus 13.6 electron volt level. So explain these observations. It's an explain question for 4 mark, and there are 2 observations given, 2 statements given. We have to explain each of. So what do we have to explain? We have to explain that why, when a moving electron with a kinetic energy interacts with this atom, it causes an electron to get excited from one level to another by absorbing some energy, but when a photon containing exactly the same amount of energy interacts with the atom, the electron does not absorb the energy, does not get excited. Why so? So first of all, as a first step, first thing, let's find out the energy difference between the 2 energy levels between which the transition is happening. So minus 1.5 minus 13.6, or you can just do 13.6 minus 1.5. It will give you a value of 12.1 electron volts. So the energy between these 2 energy levels between which the transition is happening, there is an energy difference of 12.1 electron volts. So now let's look at the first statement. The electron with a kinetic energy, the external electron, had a kinetic energy greater than 12.1 volts. It was 12.3 volts. So when this electron, so I'm writing it 1 over here to explain situation number 1. When this moving electron interacts with the atom, it transfers 12.1 electron volts of its total kinetic energy to the electron within the atom to undergo a transition from the lower to the higher state. But what happens to the remaining energy? How much is the remaining energy? 0.2 electron volts. 0.2 electron volts is retained by this external electron as its kinetic energy. So this external electron keeps on moving, but with a much lesser kinetic energy, as it transfers the rest of its kinetic energy to the electron within an atom and hence undergo excitation. So that's why we can explain that this electron can be absorbed. That's how we can explain that the electron in this atom undergoes excitation or jumps from lower to a higher energy level by absorbing some of the kinetic energy of this electron. The rest of the kinetic energy remains with the electron itself, with the moving external electron itself. Now let's try and explain situation number 2, where we have not a moving electron but a photon. And if you remember, the energy of a photon is given by hf, and photon is nothing but a packet or a quantum of energy. And we have discussed earlier that a photon can be either completely absorbed by an electron or it will not be absorbed by the electron at all. So let's look at the energy of the photon and compare it with the energy difference between the 2 levels. So the energy of the photon is given to be 12.3 electron volts, whereas the energy difference between the 2 levels, we calculated it to be 12.1 electron volts. If you compare the 2 values, they do not appear to be the same value. The photon basically carries 0.2 electron volts more energy than needed for the jump to happen, for the transition to happen. So therefore, the photon possesses a bit higher energy. So what have we learned previously? That one photon at a time interacts with one electron, number 1. Number 2, an electron will either absorb a whole photon or not absorb it. And in what situation will it absorb the photon? When the energy of a photon exactly equals to the energy difference between any 2 levels. And in this situation, the energy of the photon is a slight bit higher than the energy needed for the jump. So what will happen as a result? The photon will not be absorbed because the energy of the photon is not equal to the difference of the difference between the energies of the 2 levels, and thus the electron will remain in its state or in its original energy level of minus 13.6 eV.